No. No.
Okay, so we have 2 objectives left for today. That's absolutely. And about 100 objectives for Tuesday. Alright, so our final 2 objectives for today are adding some features to our gravitational field diagrams. So we did gravitational field diagrams back, in the fall, and we said for single mass systems, gravitational field diagrams are super simple because the gravitational force is always attractive, so you always have radial inward fields. And well, every field we ever drew looked like that, except when we had like 2 mass systems, binary systems. And the benefit and reason that we draw these fields is to do 2 things. It's to tell us the direction of the force that would act on a mass, and to give us some sense of the strength of the gravitational field, because the field line density is an indicator of the strength of the field. The field line density here is greater, right? The lines are closer together. That means the field strength is greater here, and the field strength is weaker here. And we know that because we're further away, but that's an added benefit of drawing the field lines. Okay, so we're going to, let me just make sure I don't skip stuff. So gravitational field lines are always point inward, since gravity is always attractive, and the field line density is proportional to the strength. So we are going to add something to our field diagrams called equipotential surfaces. So what does equi mean? Yeah, equal, right? And what does potential mean? Gravitational potential, right? So an equipotential surface is marking areas of equal gravitational potential, right? And gravitational potential, as we said earlier today, negative Gm over r. So if we're dealing with a single planet as the source of our field, the only thing that's going to really affect the gravitational potential is our distance from the planet. So for a single mass system, our equipotential surfaces are just going to look like circles around our planet. Okay? So these 3 kind of dashed dotted lines are 3 equipotential surfaces around the Earth. I like to give somewhat realistic values when I put these in. But that's a statement, so I'm going to use arbitrary units. But maybe this one close to the Earth is like negative 40. Maybe this next one out is like negative 30. And maybe this one is negative 20. Okay? So everywhere along this dashed line, a mass would have negative 20 whatevers of gravitational potential. All right, so when we do a pause and ask if there are questions about why these equipotential surfaces are circles. Right? Because on this side of the circle, we're the same distance away as we are on this side of the circle, and the only thing that would change the value is our distance from the thing. Now, a couple of additional features of these surfaces are, first of all, they would always be at right angles to our field lines. Okay? If our field lines point straight in, and our equipotential surface makes a circle around our planet, then the field lines and the equipotential surfaces always meet at right angles. And then the other thing that's of some importance is that as long as we have a constant gradient for gravitational potential, the surfaces should get further apart as we move further away from the Earth. It should take more space to get that same change in potential. Patrick?
So why would any surface not be equipotential? Wouldn't it make sense that the same distance?
Yes. Yes, but we don't always have we don't always have a single big thing. Sometimes we have overlapping gravitational fields.
Okay.
So then it would complicate things.
So we just have to be one gravitational field that's not affected by another.
Right. Right, so if we have a binary system, and I do want to look at that, then that's going to prevent us from having a circles. We can look at that. Yeah, Miles?
So, is the goal to make them at equal intervals, so like 40, 30, 20, or can they?
Every time I've ever seen it.
Okay, because otherwise couldn't any point have a circle at that point?
Yes. You could draw, so you can draw a circle anywhere around the Earth and call that an equipotential surface, yes. And that's fine, like that's meaningful, that's helpful. And on my next slide, I'm commenting on it. Now, down here I've got another sketch, another cartoon. And this is the surface of the Earth, but we're way zoomed in, right? So here's some trees, here's somebody, and we have these blue arrows that point down. What are those? Those are gravitational field lines, right? And so again, all that the gravitational field does is it shows us the direction that the gravitational force would act on some mass, right? So if we drop our dry erase marker from right here, the dry erase marker would feel a downward force, and unless we gave it some tangential velocity, it's going to go ahead and just follow that field line down until it runs into something, until it hits the surface of the Earth. And what are these horizontal lines? Equipotential surfaces. We've been saying since probably last November that if we hold something at a given height and move it just horizontally, we don't have to do any work to it. It doesn't take any work. I'm not doing any work to this dry erase marker. I'm not doing any work because it has the same gravitational potential energy as I move. It has the same gravitational potential. It's not leaving its equipotential surface. So we can move anywhere we want along this equipotential surface, and it doesn't require any work. We're not giving it any additional potential energy so long as we stay on that equipotential surface. You might also notice that even on this zoomed-in version, the field lines and the equipotential surfaces meet at right angles. I did because. Okay, sure, yeah. Oh man. All right. So, other questions about equipotential surfaces before we just do a tiny bit more? So I think I already said this, but again. Right? It does not take any work to move along an equipotential surface. It only requires work to move off of that surface. All right, now the other thing I'd like to do in our remaining 7 minutes here is actually do something a little bit outside the scope of our curriculum. Yeah, Patrick, go ahead.
So it's like the equipotential surfaces. Is that like, I know like the energy level is like that of the electrons.
You're not going to get me to say yes because we now know enough. We now know way more than enough to recognize that the electrons don't follow these nice little circular orbits, and they. So is it like that? Yes, it's like the simplified version of that you've been told before. But in reality, it's not. All right, so I'd like to spend probably our last few minutes today talking about one other way of kind of thinking about these potentials. And it's something I think we've all seen before, maybe heard about before. So sometimes we hear about gravity wells or potential wells. And sometimes we see figures that kind of look like this one. What do we often see figures that look like this in association with? Black holes. Often we see something that looks a little bit like this when we are attempting to understand black holes. So a black hole, as we know, is just a thing that has an enormous gravitational field strength, right? Even relatively far away from it. So obviously, if it has a big field strength, things can have large negative gravitational potential energies if they're near the black hole, and have large changes in gravitational potential as they undergo relatively small changes in their position. So what this is actually an attempt. Let me turn the lights off so you can see it better. This is an attempt to show gravitational field lines and equipotential surfaces emanating from a mass down here, right? So like these things. Oh, why can't I draw if I'm on this side? so used to standing. I stand on this side because I feel like I can hide the board from less people, whatever. These are our field lines essentially, and then these circles that go around it are equipotential surfaces. But what this is trying to show is just a very narrow range in direction, a range of angles, range of directions that are emanating from this mesh. Right? We would have another one of these maybe at every direction. It's not just going in that one direction. This is really just trying to show that the field is weakening as we go away. Right? That's why these surfaces are kind of ballooning out as we get further away from the mass. So I do have like a 2-minute video that shows this a little bit and gives one context of taking advantage of this a little bit. It's really something though that we encounter in like astrophysics only, because that's really the only place that we see effects from large masses. All right, so let me get this. I think it's only 2 minutes. And then if I'm right that it's only 2 minutes, we'll come back and maybe consider binary systems in our last minute or so. Must not have turned power on. There's just no volume yet, I think.
To understand why the moon is so important to the Earth and to the exploration of space, let's consider a new way to view the solar system. We'll turn the solar system on its side and imagine that it is a giant tabletop. Objects on the tabletop are in free space, and it takes very little energy to move around once there. Wells in that table show the energy needed to get into space from the sun, the planets, and other bodies. The more massive the object, the deeper the well. It takes enormous amounts of energy to climb up out of the deep planetary gravity wells to get to the plateau of free space. But although we Earthlings are gravitationally disadvantaged at the bottom of the deepest planetary gravity well in the inner solar system, we live right next to a more practical source of space materials, the moon. In contrast to the Earth's deep gravity well, the moon sits in a gravity dimple. If the Earth's gravity well is 22 steps deep, the moon's gravity dimple is only one small step deep. Most of the cost and danger of spaceflight comes from the difficulty of crawling up out of the Earth's deep gravity well. Instead of using Earth materials for construction in space, we can build space stations, power satellites, or spaceships using raw materials launched over the curve of the moon's gravity dimple, and let these lunar materials roll downhill to high orbit around the Earth.
All right, so there's a little interesting context that if we can extract materials from the moon, it saves us some money and energy.
Wouldn't we have to get the stuff out?
No, we'd have to, the whole point of this would be mining materials.
No, I know, but getting the stuff to mine it. You
Yeah,
gotta get to the.
sure.
Absolutely.
It's a lot less massive
Okay, now I actually skipped this in my other section, so what I should do is stop this video, start a new one, so I can tell them they need to watch this last one.